head seminar meeting of the semester. I'm glad to see many of you here in person and online. We have today as a speaker Dr. Ioanna Psaradaki, who is currently postdoctoral research fellow at University of Michigan, so Department of Astronomy. She obtained the PhD in astrophysics in 2021 at University of Amsterdam and Xray in the Netherlands. And then and before that, master in physics at University of Crete in Greece. The primary research area is laboratory experiment and high-resolution X-ray spectroscopy of interstellar dust. In the past, she has also worked on optical polarimetry of molecular cloud filaments and accretion disk properties of low-mass X-ray binaries. She joined the University of Michigan in February 2021. So let me remind you that we are recording this talk. So if you, for the people online, if you don't wish to be your video to be recorded, this is the good time to turn it off. And so I think with this introduction, I'm done. So Ioanna, please, the floor is yours.
So hi everyone, thanks for the introduction, and thank you very much for arranging this seminar for me today. I was told that I can use all the 40 minutes of today, but I won't do that. I'll probably speak about 30 minutes or maybe a little bit less. I will talk about interstellar dust, and in particular, I will try to explain how do we combine laboratory experiments with high-resolution X-ray spectroscopy to understand the chemistry of dust grains. But let's first set the stage. So interstellar dust is ubiquitous in the galaxy. It's really important for many astrophysical processes. For example, it enables molecule formation or even to cool down interstellar clouds. It is characterized mainly by its chemistry, chemical composition of the grains, and the lattice structure. And by lattice structure, I mean what we call the crystallinity, and this is simply how the atoms are organized into the dust grains. So for example, we can have the crystalline grains where the atoms are in order and the amorphous grains where the atoms are disordered. And mainly we expect to see amorphous dust grains in the ISM because the harsh environment would destroy the crystallinity. Also, usually dust grains are distributed as a parallel, and these are the typical grain sizes that we expect to see, about 1 nanometer to 0.5 microns. Now the question is, what are exactly the dust properties in the interstellar medium, and how do these change according to the different environments that we have in the ISM? What do we know today about the chemistry of interstellar dust? So we know that dust is mainly composed by carbonaceous material, for example, in the form of graphite or PAHs, and silicates. I'm going to talk a lot about silicates here. So silicates is a group of minerals, mainly that include magnesium, silicon, oxygen, and iron. And there are two famous groups of silicates, the olivines and pyroxenes. So the difference is that the main difference is that olivines have got 4 atoms of oxygen and pyroxenes have 3 atoms of oxygen. Keep that in mind. I will go back to this terminology at the end of the talk. We can also have oxides in dust, and one famous oxide is, for example, what we call magnetite with this chemical composition, and this has got ferromagnetic properties, so it's an interesting mineral. And also we have sulfates, so basically some sulfur bound with iron, and we could even have some metallic particles, metallic iron particles. So all these elements that are included in the dust grains are also in the crust of our planet, of course, in Earth. So the crust of Earth is mainly composed by oxygen and silicon, but we also have, for example, iron. And in this talk, I will focus on oxygen and iron, so the oxygen and iron content of interstellar dust, because there are still some open issues, interesting issues to resolve. Let's see what's the issue with oxygen. So oxygen, we know that is one of the most abundant elements in the galaxy, very important for life here on Earth. And it comes in many different forms, neutral, molecular, ionized, and into interstellar dust as well. we expect to have a mild depletion of oxygen into interstellar dust. However, we are still missing some oxygen. We cannot find all the oxygen that we would expect, especially in the dense environments of the ISM. And this is illustrated in this plot here, when you can see the oxygen abundance. The maximum value here is the maximum we expect to see. And here is density, different density environments in the ISM. So in lower densities, oxygen is mainly in neutral form, neutral gas, but in denser environments, the contribution of CO gases, ices, some gas, or dust cannot account for all the amount that we expect to see. So where is it? In which form? What about iron now? We know that a large fraction of the interstellar iron is locked up in dust grains, about 90%. And also most of it, it has been found that most of it is formed in supernova type 1, and it is ejected in the ISM in gaseous form. And this is what is illustrated here in this plot. If we see at this part of iron, so it shows the abundance of its elements, and that is coming from the different sources. We have AGB stars, core collapse supernova, and supernova type 1. This normalized according to the amount that you see, the amount of iron that you see from supernova type 1. So we see that basically it mainly comes from that source. So if most of it is ejected in the ISM in gaseous form, but then we find that it's basically 90% depleted, so then the depletion takes place in the ISM. And what is interesting to know is what form does solid iron takes, because then maybe we can understand how it condenses, how iron condenses in the different interstellar environments. And it should be locked in some of these minerals that I explained before, either silicates or metallic iron, magnetite, or even sulfates. So can X-rays give us an answer to this question? The good news is yes. Because we can study absorption spectrum. So how does this work? The idea is very simple, it has been used a lot in the past. So in the galaxy, we have a lot of bright sources. We are using mainly low mass X-ray binaries because we don't want to have complicated spectrum with emission light from winds, for example. That we use them as a lighthouse. So they light our way into the ISM, that there is a lot of gas and dust, and what we observe with the X-ray satellites is an absorption spectrum that brings both the information of the gas and dust in the line of sight. But how do we study the dust from the X-rays? So we study them through the X-ray absorption fine structures. So in the case of gas, let's take the simple case of a single atom here. When a photon interacts with the atom, we have the absorption probability at a certain energy or cross-section. When we have the dust, we have multiple atoms together. So the ejected photoelectron will interact with the neighboring atoms. And therefore, the wave function will be modified due to constructive and destructive interferences. And what we will get around the photoabsorption edge is these wiggles here that are called Xray absorption fine structures. And these are this gives us basically the shape of these features can tell us what is the dust chemistry in the line of sight. Now, historically, dust has been studied in the infrared, for example, which give great results. But what are the advantages to study the dust grain composition from the X-rays? There are a few. So first of all, we have the photoabsorption edge of most of the elements that compose the dust grains in the X-ray band. So we can study directly these elements. And also because the transmission of X-rays depends on the column density of the material, we can study different environments in the ISM. So this is what is illustrated in this plot. So this is the column density and this is the transmission. And you can see, for example, for low column densities 10 to the 19, 10 to the 20, we can see the carbonates. For higher column densities, about 10 to the 21 in CZS, we can get iron L and oxygen K edges. If we go higher, about 10 to the 22, we can get magnesium and silicon. And if we want to study really dense environments of the ISM, we can try to study the dust in the around the iron K edge. So which of these edges we can study right now? Luckily, most of them. And again, we want to study the X-ray absorption of fine structures around these edges. So we study the oxygen K, iron L, magnesium K, and silicon K edges using Chandra and XMM observations. And in the future, there will be missions, for example, the mission concept of Arcus, where will enable us to study the dust in the carbon K edge, and also Athena will enable us to start to probe the iron K edge. I will come to this at the end. So now, in order to study the X-ray absorption of fine structures, we need models. We need dust extinction models in order to fit high resolution X-ray spectra. And for this reason, we performed the laboratory experiments. This is an experiment that has been done during my PhD in the Netherlands at Xray. And this is a work from many people from there. And basically, what we did is that we had some dust samples with different chemical composition, and we went to the laboratories in Europe to measure all the dust in all the edges where we can study with high resolution X-ray spectra. And my collaborators went studied the silicon and magnesium edges using synchrotron facilities in France. And I went in South Spain to study basically iron and oxygen. I will briefly show you the results from the silicon and magnesium edges. So Rogantini and Zeher studied the dust grain chemistry using the silicon and magnesium edges for a number of sources along the galactic plane. And what they found was that this compound, the amorphous olivine, represents most of the dust grain chemistry in these dense environments of the ISM. And they found an upper limit of dust crystallinity of about 30%, depending on the line of sight in the galaxy they were looking into. But let's go now to the laboratory experiment of iron and oxygen. So, as I said, we went to South Spain in a laboratory. We used the electron energy loss microscope facilities there. It's this big microscope. And we had with us about 20 dust samples with different chemical composition. Basically, we had these small flasks with us that contained the interstellar grains. And we were aiming to measure those. So the dust samples are basically silicates with different magnesium to iron ratio, for example, oxides and iron sulfates. Some of them were natural, so they were extracted from meteorites, but most of them were synthesized in a laboratory in Vienna. And most of the samples come both in crystalline and amorphous form, so we can study also the dust crystallinity. Now, the first part of this job is, of course, to acquire the laboratory measurements. So this is the heart of the microscope we used. And this is the dust samples that we basically locate on a very small carbon grid, if you can see here, so that we have this small carbon grid, and on top we put some dust particles. And then we place this here, where there is an electron beam and interacts with this dust sample. What we measure is the loss of the kinetic energy of the beam because of that interaction. And then the transmitted electrons will be sorted according to the kinetic energy and with a high resolution X-ray spectrometer. And we're going to get a spectrum, what is called the electron energy loss spectrum. A little bit about what you see here. So we have the zero loss peak, where it's basically, it gathers the events where we have no loss of energy, because we basically take that with an empty space and it's used for calibration purposes. And at higher energies, we have the edges that we want to measure, oxygen and iron. And that are also these elements characteristic of the dust sample composition. And here you see a region of interest on the dust sample, where the color is the thickness ratio. So now, great, we have all the laboratory data for all these 20 samples. We need to translate this laboratory spectrum to something that is useful for us, which is the dust extinction cross-section. So I won't go into detail about the calculations, but very briefly, after acquiring the laboratory spectrum, we're able to compute the refractive index. And from there, we can basically calculate the dust extinction cross-section. We choose a preferred X-ray fitting package. In our case, we use SPECS. SPECS is an X-ray and UV fitting package that is made in the Netherlands. There are plenty of others, and we hope at some point that these models will be available to the public, so they can be used regardless of the code. And then we fit our absorption spectrum. To calculate the dust extinction cross-sections, here we use the miscattering code, which assumes spherical dust grains. And because, of course, we need to assume a dust size distribution, because dust grains don't have only one size in the ISM. They are described by distribution. And in our case, we use the MRN. So here you can see the resulting cross-sections for the oxygen K edge. So this is the extinction, the resulting extinction, and this is the scattering and absorption component. For the MRN, which has got these grain sizes, basically, integrate over this grain size. And this is the dust size distribution that basically we're using for the analysis that I'm going to show you in a bit. Now we are preparing our work where we try to understand how many larger grains we have in the ISM. So we extend this limit of the MRN to larger grains. And we have calculated the extinction cross-section, and we see that the scattering component dominates while we have the absorption suppressed. But this is a work still in progress, so hopefully we'll have some explanation and some results from this soon. Now, we have calculated the models, and we are able to apply them to high-resolution X-ray spectra. We're very thankful to the very rich archive of Chandra and XMM Newton because we can look for sources and great spectra there. And in particular, to fit the iron edges, we use Chandra HEDG data, and for the oxygen K edge, we use XMM Newton data from the reflection grating spectrometer, or RGS. This selection is because we want to have the maximum spectral resolution around these edges in order to fit and identify the dust features. So we're looking into the archives for sources that are suitable for our work. We have some criteria. Well, first, we choose low mass X-ray binaries, as I said before. Of course, we need to have availability in both XMM Newton and Chandra archives. They need to be bright so that we have enough signal to noise. And also, we need to have the proper column density in this line of sight so that we get enough optical depth in both oxygen and iron. And this is the sample that we came up with. Here you can see how they're distributed along the galactic plane. This is a dust emission map. And we have splitted these sources into different bunches. So I'm going to show you the results that we got from this first sample. And we are now working on a second sample. The sources here have got very known ionized absorption as well. So that complicates the analysis. Also very interesting, but it needs a little bit more careful fitting for the ionized absorption. And for all the spectral fitting that I'm going to show, we use the available models in specs. So this is an example of a spectrum in the iron L edges using Chandra-Hegel G spectra, and in the oxygen K edge using Xray Newton RGS data. So basically what we do is that we fit these edges simultaneously by using different continuum model, because of course they are taken in different epochs. And then we add some components in order to fit the gas. And for that we use basically a model that is included into specs, where it's a physical model. So it calculates an ionization balance according to some column density and temperature that you can fit. And then on top, we add the dust model to see how much of the absorption dust takes. And for that, we have the new dust model we have just calculated. So here you can see in the iron L edge that here we have the transmission. The dust basically dominates the fit in the iron. While we have still some contribution from gas, mainly iron 1 here. In the oxygen, the situation is a little bit different because we have a lot of absorption from oxygen 1, for example. And we have also many different species, also from ionized species. As you can see here, we go from oxygen 1 to oxygen 7. So the oxygen K edge is actually a great laboratory to study different phases of the ISM. And here again, you can see transmission. This is the gas component that here it dominates the fit, but we still have some contribution from the dust, which is a broader component that helps the absorption. And mainly we notice that it fits better these residuals here, these features here, because this is where the scattering component of extinction arises. So we do this job for all the samples that we have. But what was the question is, what is the chemistry of interstellar dust? So we have to fit with all the different compounds that we have now from all the different models. And basically, the dust model that there is in specs allows us to fit about exactly 4 dust compounds at a time. So we are fitting with all the different possible combinations that we can have. So we have more than 1,000 different fits of dust. So after doing this job and fitting with all this, we have come to some conclusions about the dust chemistry in the line of sights we studied. These are average properties that we get from all these diffuse line of sights that we probed here. So we found that the dust chemistry is mainly characterized by magnesium-rich amorphous pyroxene with this chemical formula here, and some iron metallic. We find an upper limit of crystalline dust here of 15%. From the infrared, it was found that the upper limit of crystalline dust is about, I think, 2%, if I'm not wrong. Strictly speaking, we are consistent because it's an upper limit, but if there is a discrepancy between the X-rays and the infrared, maybe because with X-rays, we can penetrate the grain and we can study crystallinity in partially glassy materials, but we still keep some short range order of atoms while the long one is destroyed. So now, back to the question, what form does solid iron take? We found that about 40% is in metallic form, metallic iron, while 60% is in silicates. Now, what about oxygen abundances and oxygen and iron abundance and depletions? We found that about 10 to 20% of oxygen is in dust form, in solid form. That depends on the line of sight. that we study, and we find solar or maybe above solar abundances of oxygen. And about iron, more than 90% is basically depleted into dust. And we find solar slightly under solar abundance of iron. And going back to the oxygen budget problem that I introduced before, we figured that with the line of sights that we study here, we basically probe a diffuse medium. So where we are consistent basically with this work because we don't have an oxygen budget problem. So maybe in the future we'll be able also to probe denser environments of the ISM from the X-rays. Since I said about the future, I have picked a couple of preferred missions, X-ray missions, and how they will help us to understand better the dust chemistry. So for the oxygen and iron that I studied here, the concept mission of ARCUS will be basically great. So you can see here a simulation in the oxygen key edge of the bright source Cygnus X2 with ARCUS. First of all, you can see that with this great spectral resolution that ARCUS will have, we will be able to observe basically a forest of lines that come from many different neutral and ionized oxygen species. But we will also be able to disentangle much better between the gas and the dust phase from this edge alone, which again is challenging because there is only about 10 to 20% of oxygen depleted into dust. Now with ARCUS, we will be also able to probe the carbonaceous material of dust grains. This is a simulation in the carbon key edge, and there are different compounds and how we will be able to distinguish among them. But what might be interesting with ARCUS to study for the carbon key edge is to see if there are carbonates. Basically, recently it was suggested that carbonates, which is basically this mineral has 3 atoms of oxygen for 1 on carbon, could be a possible solution to the oxygen budget problem. So, because we can get a lot of oxygen without over depleting, for example, carbon, there will be a transition there. We need, of course, to find the source. That is the challenging thing, but maybe there is this possibility. And then there is, of course, XRY and Athena. So XRY will give us great resolution in the silicon key edge. And here you can see a simulation in the silicon key edge and the different dust minerals here. And also this peak here is the scattering component of extinction, which is sensitive to the grain size. So we will be able to study with great accuracy the dust grains from this edge. But also with Athena, we will be able to study the iron K edge, the dust in the iron K edge. And that might be, it will be interesting by itself to study how iron, where iron is depleted in these dense environments that will be probed with Athena. But also that might be interesting for the oxygen budget problem, because we will study dense environments of the SM using the iron K edge. And from the best fit mineral, we can make an estimate of how much oxygen we have in dust in this line of sight. So that might be also interesting. And that's all I will leave you with my summary. Thank you.
Thank you so much, Ioanna, for this wonderful presentation. So do we have any questions from the audience in person? Anna, please.
Fascinating talk. That ARCUS system sounds really good. Definitely do that. Question about the iron, metallic iron. Normally, that's been at the like 10% level. And the logic has been that if it gets much above that, it starts becoming a interference with the cosmic microwave background. How do you have any comment on how do you explain that?
So when you say 10%, you mean the total dust column, or how? Oh, the total dust column of iron compared to the silicates is 15%. Sorry, yes.
Yeah,
this is how many iron atoms are
right.
in metallic form, and
right,
yes. So yeah, So if it is 10%, you said, then might be.
I have to look back to see what it is, but I think
Yeah.
40%
Okay.
metallic iron would be a very high number.
Okay,
You will
we
have-
can
you-
chat about this. Yeah, actually,
Okay.
that might be interesting. Yeah, yeah. Okay. Thanks.
Thank you. More questions?
Where do the samples of interstellar dust come from?
Sorry.
You mentioned using samples of
Yeah.
interstellar dust. How
So-
was it obtained?
Yeah, so these were made in a laboratory in Vienna and were sent to us. Some of them were from meteorites, natural samples, and some of them were synthesized. Mainly, I think the process is quenching of a melt, similar to how you make glass, I think. And were sent to us to measure them.
There is somebody at the University of Washington who collects interstellar dust that somehow from very high up to balloons.
Okay.
I can't think of his name, but that's what I assumed the samples came from.
No, actually, the people are in Vienna, in Germany, I think. In Germany, they are the people that make that. Interesting to know.
Question from in person? No? Amy, do you see any question from Zoom people? I cannot see.
I don't see any hands raised and I don't see anything written in the chat.
I have a question. This is a little off topic, but the a to the minus 3.5 rule, that has an explosion at small scales. So what happens at small scales? Does that go all the way down to atoms, or where does it stop?
Sorry, I don't know. You mean the small grains?
Yeah. I mean,
And
if you integrate a to the minus 3.5, it blows up at small a. So it must stop somewhere, and clearly atoms, individual atoms are a limit, but I'm wondering if the limit occurs somewhere before that.
no,
Molecules or
the
something.
limit is of the size is what I mentioned here. 0.005. So that's the minimum that we use for grain
Yeah,
size.
that's 5 nanometers, so it's
Yeah.
pretty darn small, but
Okay.
that's still some tens of atoms.
pH is where it stops. Polycyclic aromatic hydrocarbons.
Yeah, okay.
Yeah.
Okay. I'm not sure about the answer to your question, but I'd like to show you.
Actually, since you have this slide. The problem with extending the MRN, it actually fits the extinction curve beautifully. But as I'm sure you know, you use up all the dust, or you use up all the heavy metals. So what's your plan there?
Yeah, so the plan is actually to use realistic large grain distribution. So that was just an experiment to see how, basically to double check that the scattering contribution gets larger and see how it works. Yeah, but the plan is to use the non.
Thank you all. Amy, let me reiterate. Do you see any question? No, I cannot see any.
I don't see any.
Okay. In this case, let's thank our speaker again. See you in September for the next INT seminars. Thank you.
One of those things that confuse me.
We had a few people. You look around.